Now let's see what the Feynman rules for scatterings involving fermions are. Now our strategy to calculate the contribution to the scattering will basically follow what we did in the case of the scalars. Of course, the spinor nature of the fermions will cause some slight differences, but the strategy will be identical. Now, to calculate the scattering, we need, as an example, let's just look at the two-particle scattering, K1, K2 scattering into P1, P2. The T matrix element will be given by P1, P2. Let's just write the proportionality constant, time-ordered product. We will have the e to the power minus I over h bar, h interaction dt. Let's say that this starts from minus t to plus t, and then we have the k1 and k2. And eventually we will take the limit as this capital T over here goes to infinity. Now, first let's define these states. So let's define, just like in the case of the scalar particle, the single particle state to be. Now, of course, in the case of the fermions, or also the same holds for complex scalar fields, this single particle state can be a particle or an antiparticle. Now, first let's start with the case of a particle, and then we will just sketch what the differences will be for the antiparticle. Now, for the particle, this can be, the particle creation operators are a dagger, and this will be creating a particle with momentum k1. Let's also call the spin s1, acting on vacuum. And due to our normalization, we have the twice E of K1 appearing over here. Now, so we can write this as, we can just insert these matrix elements, these definitions, into our transition matrix element. So the transition matrix element will be, let's say, up to a phase, vacuum. We will have, let's just assume that all of these are particles. A of K P1. Let me also omit this S1, and I will just be using P. This P1 subscript denotes both the form momentum and the spin. And A of P2, the time-ordered product, a dagger of K1, a dagger of K2. Now, since these are fermionic operators, their ordering will also be important, but for the, for the sake of simplicity, I will just say that this state is defined by operators having the same order. So here I should change the order of these operators. So this is P2, P1. So we have to be consistent in our notation. If I had defined it, this state with a different ordering of operators, there will be just an overall sign difference, but we have to be consistent in our definitions. Now, the next thing we have to do, we will be doing, is we will just write all these operators in terms of the psi fields, Fourier transforms of the psi fields, and then we will just insert them into this time ordering, assuming that all those fields are acting at the time minus t, or for these operators over here at the time t, so that the time ordering already puts them into correct positions. But this, defining these to be at the time minus t or plus t, and putting them into time ordering, we can just use the Wick theorem for the remaining of the computation. So let's start with one of them. So we already know that we had defined the psi. The fermionic field was defined as a d cubed k divided by 2 pi cube a of k e to the power minus I k x u of k and plus bk dagger e to the power I k x v of k. Now I repeat here, This K denotes both the form, no, this K over here denotes both the form momentum and the spin. This K is just the form momentum. Here, this integral over K also actually involves the summation over the possible spins of these particles. Now here we need not the A operator, but the A dagger operator. So a dagger operator can be obtained from psi bar. This will be d cubed K divided by 2 pi cube a K dagger e to the power I kx u bar of K plus bk e to the power minus I kx v bar of K. Now if we act psi bar of x on the vacuum, what we will obtain is not that this operator over here, B, will annihilate the vacuum. So we on the only contribution from the A term, d cubed K divided by 2 pi cube e to the power I kx u bar of K, and well, let me just put the alpha over here, psi bar alpha. So the alpha, I'm taking the alpha component, and a K dagger acting on vacuum. Now let me multiply both sides by e to the power minus I p of x, psi alpha bar of x, 0, and integrate over d cubed p. And here I had forgotten the two ek factors. Okay, d cubed p divided by 2 pi cube. No, d cubed x, sorry. D cubed x. This is equal to d cubed x over 2 pi cube square root of 2ex ek e to the power minus I p minus k of x u bar of k alpha a k dagger. So now the d cubed k integral will just give me e to the power I minus I p0 minus k0 x. And now here there is also the k integral divided by 2 pi cube. The x integral, let me write the k integral first. The x integral gives me a 2 pi cube times the Dirac delta, three-dimensional Dirac delta of p minus k, u bar k alpha, and k dagger acting on vacuum. Now I can take this k integral appearing over here. These 2 pi cubes will cancel. E to the power minus I p0 minus k0 x 1 over square root of 2e p. Now note that this k0 is actually just now e of p. And u bar of p alpha a of p dagger acting on vacuum. Now p0 is well, here we are taking the integral over the three components, so I will also choose p0 to be e of p. So the exponent just gives a factor 1, and we end up having d cubed x e to the power minus I px psi alpha bar of x. This is equal to 1 over square root of 2ep u dagger p alpha a of p dagger vacuum. Now I will use the normalization of these u spinners to get rid of this u bar over here, we know that the U spinors are normalized such that U bar of P, U of P is equal to 2m. So d cubed x e to the power minus I p of x psi alpha bar of x is actually equal to, let me multiply by U alpha of p from the right. Now U alpha of p, this is 1 over square root of 2 ep. Here now U bar alpha, U alpha gives the U bar U, which is just 2m. AP dagger acting on vacuum, or AP dagger acting on vacuum is equal to square root of 2 EP divided by 2m d cubed x e to the power minus I p x psi alpha bar of x psi bar of x u of p. Now, so this state, our initial state, which we define as this K1S1, or let's say the P state, is now given as 2EP divided by 2m d cubed x e to the power minus I p x. So this is acting on a vacuum. Psi bar of x u of p acting on vacuum. And if we have more than one particle in this state, for each particle we have a similar factor creating the corresponding particle. Now let's see how this will contribute to our T matrix element. You see, we have the T matrix element was defined as, with these conventions, of course, some kind of some states acting on vacuum inside the time ordering. We will have many operators inside, both creating the final state particles and also the interactions. And on the other hand, we will also have this factor over here, 2EP divided by 2m d cubed x e to the power minus I p x psi bar of x. Let me introduce the index alpha again. U alpha p. This is not an operator, so I can just move it in or out of the time ordering. And vacuum. So this is what our T matrix element will become. Now this psi bar will be what will be creating our particle. So when we are using the Wick theorem, it should be contracted with something inside. So let's say that here there will be some spinor psi. Let's call the position y, beta. This is due to, for example, some vertex in the interaction. Our particle, this is the particle that will be creating, this is the field that will be creating an ingoing particle, and it will be connected to some vertex in our diagram at the position y. So now we will need to, they will be contracted. So we know what the corresponding contribution is. We had already calculated that this contraction, psi k of x, psi l of y, well, in this case it is, let me just, psi beta of y, psi bar of x alpha is equal to d cubed p, d4p divided by 2 pi cube, 2 pi to the 4, e to the power minus I p x minus y, this is y minus x, I p slash plus m, beta alpha, divided by p squared minus m squared plus I alpha. This is something that we had already derived in our earlier videos. So let's just look at the factor that will arise from the contraction of this ingoing particle. If we combine all these factors and the integrals with this contraction, we will get, due to this ingoing particle, we will get a integral. Let me also write down the factors: 2ep divided by 2m d cubed x e to power minus I p x psi. Now the contraction is given over here, d4p divided by 2 pi to the 4 e to power minus I p y minus x. This is p1. The momentum of the this is K1, the momentum of the ingoing particle. Minus I p y minus x I p slash plus m beta alpha divided by p squared minus m squared plus I epsilon. And so this is, we wrote this overall factor. There is the x integral is already over here, and then we have this contraction, and also we have this whole thing is acting on u alpha, is multiplied by u alpha. Of K1. Note that this is P over here, this is K, so we cannot yet use the Dirac equation. So now let's continue. This will be equal to, I can just use this, I can take out the x integral, 2ep over 2m. I have d4p divided by 2 pi to the 4, and the let me write the zero components, k1 0x0 plus I p 0x0, and then I have in the exponent minus I py, it is just this term over here, and then the remaining three-dimensional x integrals will give me 2 pi cube Dirac delta cube K1 minus P I P slash plus M times U. Now this U has the momentum K1, the beta component, divided by P squared minus M squared plus I epsilon. Now here I can use this three-dimensional Dirac delta to evaluate three of the P integrals. So that will give me 2ep over 2m dp0 divided by 2 pi q e to power minus I, k10 is ek1 minus ep. Now P just became K1, so this is K1 x0 minus IPY. Okay, so let me write this K with a prime Y. Now this K prime, I define it as P0 and K. It's not this K, K1 prime. It is not this not this K1, which has the K10 as EK1. It's the zero component of this K1 prime is just P0. So okay, now this is just a single factor. This 2 pi cubed cancel the three of these. I took the Dirac delta already, and then here I have the I K1 prime slash plus M u of k1, the beta component, divided by, let me write this as p0 squared minus e k1 plus I epsilon. Now this is also squared. So this, there's no contribution there, so this is equal to twice EP divided by 2m dp0 divided by 2 pi e to the power minus I k1 prime y I k1 prime slash plus m u of k1, the beta component, divided by p0 squared minus e of k1 squared plus I epsilon. Sorry, here I made a mistake. P0 is just P0. So this is EK1 minus P0, X0, okay. So here there is in the exponent, there is e to the power minus I. There is an extra factor of minus I EK1 minus P0, X0. So let me just write it in a slightly cleaner way. So this is equal to 2EP. This is also K1. This is the moment energy of the incoming particle, not the integration momentum. EK1 divided by 2m. There is the e to the power I k1 dot y term inside over here. There is a minus I e k1 x0 term over here, this one, this one, and what remains inside is, dp0 divided by 2 pi e to the power, let's see, plus I p0 I p0 x0 minus y0. Now this x0 is this one, p0 x0. Remember, k1 prime has the 0 component equal to p0, so it is this term over here. And inside I have the I k1 prime plus m u of k1 beta divided by p0 squared minus e of k1 squared plus I epsilon. Now remember, x0 is the time, if you go back, x0 is the time when my ingoing particle is field is acting. And it is before, by our initial definition, it was somewhere over here. You see, we put this field inside this time ordering product with the understanding that it should be far on the right, and hence it is at the time minus t or before. It wouldn't make any difference if it is before, but it should be at the time. It is earlier than any other time in this time ordering. So that is the crucial thing. So which basically means that x0 is earlier than y0. But that tells me that x0 minus y0 is less than 0. Now we can evaluate this integral using complex integration. In the complex P0 plane, you see this the integrand has poles when this is 0, or it has poles when P0 is equal to plus or minus e of k1 squared minus I epsilon. That is the positive root. The positive root has a slightly negative imaginary part. So it is one of the poles is over here, the other pole is over here. And we are integrating over the real axis. Now we have to close the contour somehow, either above in the complex plane or below the complex plane. And the choice is dictated by the fact that x0 minus y0 is negative. So for the contribution from this semicircle, whether it is above or below, to go to 0, we see this is negative. If P0 has a positive imaginary part, I times I would make a negative, another negative over here, so the exponent will have this term will have a positive infinity imaginary part. So that's not what we want. What we want is the exponent to have a negative infinite real part in these when we are closing it. But that since this is negative, that tells us that we should close this when over a contour where P0 is negative. So since when P0 is negative, let me just write it explicitly. Let's say that P0 is a real part of P0 plus I times the imaginary part of P0. So the e to the power I P0, x0 minus y0 is equal to e to the power I real part of P0 times x0 minus y0, and e to the power minus imaginary part of P0, x0 minus y0. But keep in mind that x0 minus y0 is negative. So if we want this term to be 0, then imaginary P0 should also be negative. That tells us that we should evaluate this integral over a closed contour which closes below from the lower complex plane, but that tells us that we only have to take this pole into account, not the other pole. Well, that was kind of expected, because if you remember our earlier videos, this pole in the positive P0 line corresponds to the particle, this one corresponds to our antiparticle, and here we are looking at the particle. So if we close it through this line, the residue will be only from, let me just write the contour. Now we should calculate the residue here, and the residue of, so we need the residue of e to the power I P0, x0 minus y0, I k1 prime slash plus m u k1 beta divided by P0 squared minus e of k1 squared plus I epsilon. This residue at P0 is equal to plus ek1. Well, since I am already calculating the residues, I can just omit these epsilons. I will take it to be 0 anyway. So this is equal to limit as P0 goes to ek1 of e to the power I P0 x0 minus y0 I k1 prime slash plus m u of k1 beta divided by P0 plus ek1, which is e to the power I ek1 x0 minus y0 I. Now here I'm just putting P0 to ek1, so that just converts k1 prime to k1 without the prime, k1 slash plus m u of k1 beta divided by 2 e of k1. Now note that k1 slash minus m u of k1 is 0, so k1 slash u of k1 is m times u of k1. So this is equal to here, this k1 slash acting on u of k1 gives me m, so we get I times 2m divided by 2e k1 e to the power I k ek1 x0 minus y0. And let's see, here we have u of k1 beta. Now we can put everything together. So you see, this is what we were trying to evaluate. And so this is equal to 2ek1 divided by 2m. Well, let me just write some of these factors. From the residue theorem, we have a 1 over 2 pi I. And there is a I 2m over 2ek1. There is e to the power I ek1 x0, but that cancels this one. And then I have e to the power minus I ek1 y0. Well, but that just gives me e to the power minus I ky. These are the 4 vectors. Now, then we have this, here we have a, no, sorry, the residue theorem tells us there's a 2 pi I in the numerator, not the denominator. And what else do we have? There's this u of k1 beta. And keep in mind that here, you see, the contour is going clockwise. So this 2 pi I should be minus 2 pi I. It would have been plus 2 pi I if the contour was going counterclockwise. And so those are all the factors we have. Now you see that these 2 ek1s cancel, these 2 m's cancel. There is a, okay, here there is a 2 pi. So let me also divide by 2 pi. This 2 pi cancels this 2 pi, this I and minus I, they cancel each other. So we end up having a e to the power minus I ky u of k1 of beta. So this tells us that if we have a vertex and there is an ingoing particle into that vertex with the momentum k1, and these vertices appearing over here, the legs of the vertices will have the spinor label. So if the spinor label it is connected to is beta, then there is a corresponding factor of e to the power minus I ky u k1 of beta. Now, there are a couple of things to pay attention to. Well, if you remember the scalar case, for an ingoing scalar, this was what we had only. Now there is also the spinor, so we have this additional factor. Now we can repeat this process. Let's say for antiparticles, let's just go over the possible changes. For antiparticles here, we will have, at least if one of the particles is an antiparticle, we will have a B appearing over here. So we will be using the psi field rather than the psi bar field appearing over here. And psi field will contain a V instead of a U. So for an antiparticle, we will end up having a factor V. And the exponent, you see the exponent over here is, will be the same basically. You see, if we want the AK dagger term, we use the psi bar. This is the exponent. If we want to use the BK dagger in our, if we want to create an antiparticle, the exponent is still the same. So if we have all the remaining derivation will be identical. So this is for a particle. So if you have an ingoing antiparticle, then you have e to the power minus I, okay, this is k1y, and also this vertex is at the point y. And we would have v k1 beta. This will be the main difference. Now for the outgoing particles, well, again the derivation will be more or less identical, but we will be doing the same derivation with the A fields over here. And if you want to extract the A fields in the kit, you need this this term over here, you need the psi. So if you have a particle in the outgoing state, you will use this term. So you see the exponent changes sign. And again, you have the u, but to obtain the a, for example, you would be multiplying this u by u bar. You see over here, in order to obtain the a dagger, we had to multiply psi bar by u. Here, in order to obtain a, we have to multiply psi bar by u bar. So those will be the changes we have. So we go down. So if you have an outgoing particle with momentum, let's say, again, let me just use the same symbol for momentum, from a vertex at the point y with the spinor index beta, you would get e to power I k1y u bar of k1 beta. And if you have an antiparticle, with the same momentum k1, you will get e to power I k1y, but this time it will be v bar of k1 beta. So basically this will, with the previous weak theorem, this allows us to calculate all the relevant matrix elements. Now let's just note one point. You see, if we are looking at, let's say, two particle scattering, we had the AK dagger, AK1 dagger, AK2 dagger, vacuum, and here we had the time ordering, etc. And we said, okay, what we did was, okay, here there's the vacuum, there are some other operators. So we expressed these in terms of psi fields first, and they are just contracted with some vertices appearing inside the time ordering product from the interaction. So let's say that we have a psi of x over here and the psi of x1, psi of x2. Now we have a term, a diagram resulting from this contraction, but we can also have another diagram that results from this contraction. Now, if you compare these two, I can just strictly, in fact, one thing I can do is I can just imagine exchanging the position of these two operators. But if I exchange the position of these two particles, then it will become identical to this one with K1 and K2 exchanged. It will be identical to this one, but due to the fermionic nature, they will acquire a different sign. So one thing to pay attention to when using Feynman rules to calculate such diagrams is, for example, if you have a process and there is a vertex over here, another vertex over here, let's see, there's some vertex, there are two vertices appearing over here. You can have such a contribution, or you can have such a contribution. Well, these circles just denote some other part of the diagram, which can be anything. So your ingoing particles, your outgoing particles, or it can be the other way around. If you only change these particles, you get an additional minus sign because of this exchange over here. So that is something that should be, well, this is a relative minus sign, and hence this minus sign will be important. So that is something to keep in mind. This diagram, And this diagram, they are not just obtained from, their contribution cannot be just obtained from one another by just exchanging K1 and K2. You also have to insert a minus sign to obtain the contribution of this diagram from this one.